Hey guys, it's Margot at Lanterna here. Welcome back to another Applications and Interpretations maths video. Today we're going to start looking at integration. We'll be starting off with some of the standard level content, specifically point 5.5 in the syllabus, and we'll be looking at indefinite integrals, definite integrals, and the fundamental theorem of calculus. So really building that fundamental basic knowledge to tackle that integrals part of the syllabus. I hope you find this useful. Let's understand the idea of what the principle of integration is and integration as anti-differentiation. So remember, we usually learn about integration following learning about differentiation. So if you remember, if we have a function f of x, then if we differentiate f of x, we get the derivative, which we denote f dash of x. Now, integration then is essentially going the opposite way to differentiation. So if we integrate our derivative, we get back to our function f of x. Similarly, if we integrate our function f of x, we get this function capital F of x, which we call the antiderivative, because again, integration is the opposite of differentiation. That's really what we have to keep in mind here. So some standard integrals then. We've got two columns of integrals. I've copied them directly from the formula booklet. The ones on the left are relevant for both standard and high level, and the one on the right is for high level only. Now, these are the integrals that you need to be aware of. And whilst you might not remember all of them off by heart, I would really strongly encourage you to become super familiar with them, because I promise it's going to pay off in the long run when you start to solve trickier integrals. So once you do a lot more practice, you will start to remember these quite naturally, but remember to just revisit them every now and again. One thing I want to point out here is this C. Whenever we have something called an indefinite integral are where the integration boundaries are not specified. So indefinite integral is when the integration boundaries are not specified. By integration boundaries, we mean that there's no number above or below the integral telling us between which points to integrate. It's just a general integral. Whenever we have an indefinite integral, this is accompanied by something called the integration constant plus c. Now, what is the integration constant? It is added to all indefinite integrals. So some properties of integrals then. First of all, this top property, if we have a function multiplied by some constant number a, what we can do is we can always take that constant number out to the front of the integral. It doesn't change the integral. The constant multiplies just in the same way inside and out of the integral. Second property, if we have two functions summed together in the integral, we can always split that integral up into the sum of these integrals of these different functions. So let's just see with a relatively simple example how we can apply these properties. X cubed plus 2x squared plus 3. We want to integrate that with respect to x. So first of all then, if we use property 3, we can split this one function up into 3 different integrals, right? Integral of x cubed plus integral of 2x squared plus integral of 3 dx. Using property 2 then and applying it to the second and third integral, 2 and 3 are just constants. So what we've done is we've taken them out to the front of the integral. Finally then, using the formula for the integral of x to the n from the previous slide, we find that overall this integral is x to the 4 over 4 plus 2x cubed over 3 plus 3x. And remembering, of course, our integration constant c right here. I want to quickly just show you why this final integral is 3x, or 3 times x. This integral of dx, this is the same as the integral of x raised to the power of 0 dx. right? Because x, any number or any variable raised to the power of 0 is just 1. So this is equivalent to the integral of dx. And now with this, we can apply that integral rule for x to the n, where n in our case is 0. We see that this is equal to x to the 0 plus 1, right? X to the n plus 1 divided by n plus 1, 0 plus 1. So overall, we have x to the power of 1 over 1. Hence why that integral of 3 times dx is 3x. Now, finally, one question that you might have is, well, when we solve 3 different integrals, surely we should get an integration constant associated with every integral that we solve. So shouldn't this be, well, the integration constant of the first integral plus the integration constant of the second integral plus the integration constant of the third integral? Well, yes, that's correct, but this is just an arbitrary constant. We don't attach a value to it. We don't know what it is equal to. So therefore, what we do is we combine these 3 integration constants into just one integration constant, capital C. So yes, every integral has an associated integration constant, but when there's multiple, we can just combine them into one because we don't know anything about its value. It's just representing that there is some additional constant which relates to the ambiguity of this integral. Perfect. Okay, moving on then to definite integrals. So we said before that indefinite integrals are where we do not specify integration boundaries. Definite integrals then, as the name gives away, we do know between which boundaries we are integrating, and those boundaries are denoted by a lower boundary at the bottom of the integral and an upper boundary at the top of the integral. So a definite integral, it computes the area of a graph f of x between points a and b. So conceptually, that is what a definite integral is. We can see that on a function here, but if we have a function f of x in red, then the area between a and b is found by computing the integral from a to b of f of x dx. So it's really important to have that conceptual understanding of what an integral is. And there's a couple properties associated with definite integrals. Now, it's probably unrealistic that you're going to remember 5 of these properties of your exam. Well, don't worry. If we know that a definite integral represents this area under a curve, we can actually quite easily convince ourselves why these properties hold true. So let's just go through them and think about the key ideas behind all of them then. So first of all, the integral from a to b, f of x dx, is equal to the negative integral from b to a of f of x. So what we've done is we've switched the integration boundaries and introduced a negative sign. Well, if we think about why that is relating to the integral as the area under a curve, if we're finding the area going from a to b, we're going in the positive x direction. Whereas if we're finding an area from b to a, we're going into the negative x direction. So if you imagine we're going in the opposite direction, in going from a higher x to a lower x, that area is going to be negative, essentially. So hence why going from switching those integration boundaries, we're now going in a negative x direction, hence our integral will become negative. Second property then, the integral of f of x dx from a to a, that's essentially finding the area of a line, right? The integral from a to a. Well, we know that a line doesn't have an area, right? An area is 2-dimensional, a line is 1-dimensional. So there's no such thing as the area of a line. It's infinitesimally small, so we say it is equal to 0. The third integral, well, that's just very similar to the properties we learned on the previous slide. For indefinite integrals, if we've got the sum of 2 functions, we can split that up into 2 separate integrals of 2 functions, keeping those same integration boundaries. The fourth one then, again, very similar to the properties we saw on the last page. If we have a constant, we can just take it out to the front. And then finally, if we have the integral from a to c, we can split this up as an integral from a to b plus an integral from b to c. And we can see that on our diagram. Imagine if we wanted to take the integral from A to C, well, that's exactly the same as the area from A to B plus the area of B to C. Moving on then to the fundamental theorem of calculus. Remembering, we denoted capital F as an antiderivative. So we say that the integral from A to B f of x dx is equal to the antiderivative, the value of the antiderivative between A and B, which is equal to the value of the antiderivative of B minus the value of the antiderivative at A. So let's see this in practice then with an example. So we have here a definite integral between integration boundaries 0 and 2, and we want to find the integral 3x squared plus 1. So just starting off with a relatively simple example so that we can really focus on how to apply this fundamental theorem of calculus. So first of all, our task is to find the antiderivative being the function which is the derivative of our original function, small f of x. So in this case, we apply our integration rules to say that this is equal to 3x squared dx plus the integral from 0 to 2 of 1 dx. This is then equal to 3 times the integral of 0 to 2 x squared dx plus the integral 0 to 2. I'm going to write this as 1 times x to the 0 dx. Then using our formula for the integral of x to the n, we see that this is equal to 3x cubed over 3 plus that second integral's x to the 1 over 1, so just x. So this is our antiderivative. We've just found the integral of our whole function. And what we're told by this fundamental theorem of calculus is that we have to put this in square brackets between 0 and 2. So it's our integral from 0 to 2 of our function f of x is equal to our antiderivative between 0 and 2. Well, what do these square brackets mean? Well, it just means we need to take the value of this antiderivative at 2 minus the value of the antiderivative at 0. So first of all, then, substituting in 2, we get 3 times 2 to the 3 over 3 plus 2. And we need to subtract this, plugging in 0. Well, we can see that if we plug in 0 into this equation, it's just going to be 0. So overall, what we get is that our function is 3 times 8 over 3. So that's going to be 24 over 3. Plus 2, which is equal to 30 over 3, which is equal to 10. So the answer, the integral of this function between 0 and 2 is 10. So we're really showing how we apply the fundamental theorem of calculus. So that was it for this short introduction to integration. I hope you found it useful. We've just been building on the basics. In the next video, we're going to tackle some more difficult methods of integration, such as integration by substitution and integration by parts for the higher level students. So in the meantime, have a look on our website or online to check out some other videos from other great tutors in plenty of other subjects such as economics or ESS or geography. I hope you enjoy them.